Welcome to lecture number 19 for ECE 461 Control Systems, Growth Criteria and Stability. Now, stability is an important property of a system. What stable means is that if I take a system and I perturb it, it comes back to where it started. For example, if I have a bowl at the bottom of a ravine, if I perturb it, it's going to roll back down to the bottom. That's stable. In contrast, unstable would be like a ball on top of a hill. If I push the ball, it won't come back, it's just going to keep on rolling. That's an unstable system. Pretty much unstable systems are useless, they break. The whole goal of control systems is to make something stable. And you don't have to have a system that's open loop stable. Closed loop is all you care about. You can stabilize systems that are unstable using feedback. That's one of the beauties of feedback. Examples. Standing up is unstable. For example, if you have too many beers and you pass out, you fall over, you've got to have that feedback system. You have to be constantly adjusting the forces and torques on your knees and ankles to keep standing up. If you do that, you can actually stand and walk and do things like that. Bicycles are unstable. When you first learned how to ride a bike, you fell over a bunch of times, skinned your knees, very sad. But after some time, you eventually learn how to adjust your weight, adjust the steering to keep the bike upright. Rockets are unstable. A rocket is essentially trying to balance on a ball of flame, the rocket. If you do it wrong, it spins out of control. There's a bunch of videos in the 1950s of NASA trying to launch rockets, and they went unstable. If you do it right, I can get a rocket to stay upright, land, and kind of like what SpaceX is doing, I can have it launch, come back and land on a nice little platform. That's all using feedback. Economies are unstable. During good times, people buy more, companies sell more. When companies sell more, they hire more people. People have jobs, get paid more, they buy more. So you have this boom cycle. Bad times, when something bad happens, people buy less, companies start laying off people. People then buy even less when they get laid off. Companies sell even less, lay off even more people. You get these boom and bust cycles. Even the Roman Empire has noticed that there were boom and bust cycles. That's how long economies have been unstable like this. You basically have a positive feedback system. Good times have positive feedback and turns into a boom. Bad times turn into a recession. The whole job of the Federal Reserve, that's your feedback system. The Federal Reserve's job is to play with the money supply and interest rates, trying to keep the economy at a nice, steady, sustainable level, right around 2-3% growth. If you have more than that, you're getting it into a boom, and you'll eventually have a crash. If I start going into a recession, they'll lower interest rates, increase the money supply, trying to keep the economy going. So with feedback, you can hopefully avoid the unstable system that's inherent in economies. So that's the whole idea of this class. Control systems actually studied throughout academia. It's studied in economics for money supplies economies, studied mechanical engineering, electrical engineering, aeronautical engineering. Pretty much unstable systems are very common. With feedback, I want to make an unstable system and turn it into something useful. The problem with feedback is I can't take a perfectly good stable system and make it go unstable. For example, when you first learned how to drive a car, what you did is you jerk the steering wheel, hit one curb, so you jerk the steering wheel the other way, hit the other curb, and keep on overcorrecting. What that does is you wind up just hitting curb to curb to curb. Eventually you learn to back up on the gain, and when you go around a corner, instead of jerking the steering wheel, you kind of gracefully adjust it so you somewhat gracefully go around the corner. In aircraft, there's a thing called pilot-induced oscillations. If you take a Cessna is open loop stable, meaning if I take my hands off the controllers, the airplane will fly itself. What pilot-induced oscillations are is that if I'm coming in for a landing and I overcorrect and start going into the ground, I'll pull back on the joystick and overcorrect and start going into the air. So I'll push down on the ground because I want to land, push down too far, so we overcorrect, start going back up again. That's called pilot-induced oscillations. The oscillations tend to get bigger and bigger and bigger, and if you don't let go of the joystick, you're going to hit the ground with a big smack. The way you fix pilot-induced oscillations is you take your hands off the controls. You are up in the feedback loop, you're making things worse. Let the airplane fly itself, and then the airplane will settle out. Again, Cessnas are open loop stable. Then you can try it again. So that's feedback. Feedback can make things go unstable. The challenge in this class is I want to use feedback. I like high gains, like from the previous lecture. High gains are good, but don't make the gains so high that I go unstable. So here's the question, or to illustrate that. Too much feedback is bad. Here's a perfectly good stable system. 3 real poles at -1, -2, -3. Think heat equation or 3-stage RC filter. 3-stage RC filter is not going to go unstable. If I add feedback, however, I can take that nice stable system and make it go unstable, close the feedback loop, and I get, again from block diagrams, the gain from R to Y, which is G, over 1 plus the loop gain, G over 1 plus G. That works out to 100 over the denominator plus numerator. Factor this, I now have unstable poles. So I took a perfectly good stable system, closed the feedback loop, and made it unstable. That's the problem with feedback. Too much gain is bad. Not enough gain is also bad. So what's the right amount of gain? That's kind of the whole goal of this class. So here's a problem for you. How do you determine whether a system is stable? Well, that's easy in MATLAB. Just input the system, find the roots. If they're negative definite, you're stable. Routh Table, what we're talking about today, also works. More interesting question, how do you determine the range of gains that result in a stable system? For that, you need a Routh Table. That latter question is kind of useful. It's a lot harder, but it is useful. For example, got a tour of Honda back when I graduated from college, and they've got all the robotic systems on the assembly line. The workers are constantly adjusting the knobs, tuning the assembly line, tuning the robots to make them a little bit more efficient. Again, this correct setting for the knobs depends upon temperature, humidity, time of day, whether the machine's warmed up or not. So they're constantly adjusting the knobs, trying to optimize it. I would like to make sure that those knobs cannot be adjusted so badly that the system goes unstable, kind of making the line dummy proof. That's one thing a Routh criteria can do. It can tell you what range of gains make it stable, what range you need to avoid. Second thing that Routh tables do for you is sometimes the system just is not stabilizable. No matter what you do, you can't make it stable. You can prove that with the Routh table. What that tells you is don't sit there and spend hours adjusting the knobs trying to make it stable. If it can't be stabilizable, you got to do something else. That comes out of a Routh table. So what a Routh table is the following. Suppose I had a polynomial. Is the polynomial negative definite? And where that comes from is kind of like this case. This is the open loop system, G. Closed loop is G over 1 plus G, which turns out to be the denominator plus the numerator. When is that polynomial stable? When is that negative definite? So here I've got this polynomial. Is it negative definite? The procedure is start with the first term, a sub n, and do every other term. A sub n minus 2, a sub n minus 4, and minus 6, and so on. When you run out of terms, just put down zeros. Now do the second term, a sub n minus 1, and every other term, n minus 3, n minus 5, n minus 7, and so on. That's the first 2 lines of the Routh table. The next step is fill in the next line. From then on, it's the same procedure over and over again. The next line looks at the previous 2 lines and forms minus the determinant of AEBF over E. The second one is minus the determinant AECG over E. And kind of notice over here, the left side is always AE, it's the left side of the Routh table, AE, AE, AE. The denominator is always E. The right side is the column just to the right. So that'll be BF goes here, CG goes here, DH goes there, and so on. Calculate these determinants, and I now have 3 rows. Now for the 4th row, take the previous 2 rows, row 2 and 3, to compute the 4th row. 5th row, take the previous 2 rows, so on and so on. Keep going until you wind up with a bunch of zeros. At that point, you're done. The Routh criteria is go back to your table and count. How many sign flips are there in column 1? Each sign flip is an unstable pole. Or the Routh criteria is to be stable, there can be no sign flips in the first column. So that's the Routh table. Probably easiest to illustrate that with a couple examples. For example, let's take something where I know what the answer is. This system is stable. The poles are at -1, -2, -3, -4. This is a negative definite polynomial. Can I show that with the Routh table? So what I do is I multiply it out and take every other term. There's 1s to the fourth, 35s squared, 24s, and I'm done. Take every other term, 10s cubed, 50s, and I'm done. Now form row number 3. Row number 3 are the determinants. Notice the left side is 110, 110, 110. That's the first column. The denominator is that entry, 10, 10, 10. And the right side is just to the right. 3550 goes here, 240 goes here, 00 goes there, and so on. Find the determinants. And the determinant would be 1 times 50 minus 35 times 10 with a minus sign. So it's also equal to 10 times 35 minus 50 over 50. That gives you 30. Over here, 10 times 24 minus 0 over 10 gives you 24. 0 minus 0 over 10 gives you 0. Kind of a shortcut. If the right side is 0, the answer is 0. If it's 24, 0, it's just that this guy comes straight down. This one you got to work for. Now that I have the third row, do the fourth row. Fourth row is take the previous two rows. Here I've got a 1030. So there's a 1030, 1030, 1030. The denominator will be 30. And the right column will be the stuff to the right. 5024 goes here. 00 goes here. 00 goes there. So these are 0. This one I got to work for. 30 times 50 minus 10 times 24 over 30 is 42. Got the fourth row. Now do the fifth row. That's going to be, again, 30, 42, 30, 42. Denominator is 42. And 24, 0 comes here. 00 goes there, gives you 24, and then zeros. Once you get all zeros, I'm done. Once you're done, then count the sign flips. I've got everybody's positive, no sign flips. This is a stable polynomial, or negative definite. And I already knew that. Where it's more useful. Suppose I had that former system that I had up here, from right here. Instead of make that 100, make that k. Gives me s plus 1, s plus 2, s plus 3 plus k. What range of k gives you a stable system? So, multiply this out and form the Routh table. The first row would be 1, 11, and that's it. Second row would be 6, 6 plus k. Both these are times a constant, so they both go in right here. And 0. Next entry. This will be 6 times 11 minus 6 plus k over 6. That gives you 66 minus 6, 60 minus k over 6, 0, 0. And a trick with the Routh tables, I can multiply a row by a constant and multiply a row by a positive constant and not change the result. So I'm going to multiply by 6 just to make the math a little bit easier. Third row's done. Next row. This is going to be these two, 60 minus k times 6 plus k minus 0 over 60 minus k gives you 6 plus k. Such when you have a 0 right here, that number drops right down. Zeros to the right makes that 0, 0. Next row, zeros to the right makes that 0. So there's your Routh table. To be stable, there could be no sign flips. So positive, positive, 60 minus k must be greater than 0, meaning k is less than 60. And 6 plus k is greater than 0, meaning k is greater than minus 6. So the range of k for stability is k has to be less than 60 and greater than minus 6, or minus 6 is k is between minus 6 and 60. A way to check, if I plug in the endpoints, I've got to have roots on the j-mega axis. It's right on the edge of going unstable. At minus 6, I've got a root at 0. That's on the j-mega axis. At 60, I've got roots at plus minus j3.3. So that checks out. And the gain I had before, 100, is too large. That gave me an unstable system. Last example. This is where it's kind of hard to do it with any other method other than Routh criteria. Suppose I've got 3 knobs to play with. This is a PID controller we're going to look at later. Now I just treat it as 3 gains. What range of PI and D give you a stable system? Again, the approach is multiply this out. And that gives me 1s cubed plus 6s squared, 11 plus ds squared, 1, 2, 3, 4, s to the fourth, s cubed, s squared, 6 plus ps plus I. Now form the Routh table. Again, this entry is going to be 6 times 11 plus d minus 6 plus p over 6. This entry, since that's the one right there in the 0, comes straight down. Next one is going to be a little bit uglier. 10 plus 6d minus 6p times that, minus that over this. 0, 0 comes straight down, then I comes straight down. So all these have to be positive. The criteria for a PID compensator to be stable are 10 plus d minus 6 over p minus p over 6 has to be positive. This has to be positive, and I has to be positive. Again, kind of hard getting that solution with any other method. But with Routh criteria, I can tell you whether the system is stable or not, and I can tell you the range of gains that give you a stable system. That's lecture number 19 for ECE 461, Control Systems, Routh Tables.